Right, so here's practice question 12, and this is to do with phase differences. And here's my little bit of a rant about IB and their ambiguous curriculum language and why I think this is not a fair question. Here we go. So let's read the question, set it up. I'll draw a picture, I'll go through some of the assumptions, and then I'll explain why I don't like it, but I can also, the correct answer is C, although I think that's pretty mean, and I don't know, it just bugs me at questioning whether or not that's curriculum. So let's take a look. Third harmonic standing wave, we're told the wavelength is 80 centimeters. It's fixed on both ends, and there's 2 points on a wave that are separated by a distance of 60 centimeters. What is the possible phase difference between the 2 points on the wave? And then we're given a bunch of options. So let's do a little picture. Here it is. It's the third harmonic, so 1, 2, 3. It's fixed at both ends, and it's what else do we need to know? Oh yeah, the wavelength is 80, so we can put these on here. So if the wavelength is 80, so from here to here is 80, that means that the whole thing, the length of this string, is 120. Okay, none of that really matters. So what's the phase difference? Well, what we learn very briefly, and let's actually look at the curriculum first of all. There's not a lot in there in terms of definitions in the curriculum. We're just told that we need to know time, period, frequency, amplitude, displacement, and phase difference. Now, the problem is there's two different ways of looking at phase difference. There's phase difference on a traveling wave, and then there's phase difference on a standing wave. And it's a little bit nuanced between the two. This wave is a standing wave, which hopefully we'll get to in a moment, justifies the answer C, but I don't like it because and the textbooks and the vagueness in the curriculum don't really get into the difference between the two. What we normally teach to kids, and I'm sure this is what you've done and what's in the textbooks, is we talk about radians, we talk about the motion of the wave, so we start to say stuff like this. We're saying, well, if you have a full wave, this is equal to 360 degrees of a rotating circle. If you were to kind of plot this as an object moving around the circle, as you normally do with simple harmonic motion, it's going to do a full rotation of the circle to get to the full wave. And if we do that in radians, that's 2 pi radians. So I've just moved the sign over there. So full wavelength going from here to here is 1 full wavelength, 80 centimeters. That's 2 pi or 360. Of course, we keep going. We say, well, at this point, this is half a wave going from here, the green dot to the green line. This is equal to pi or 180. And we can keep dividing it up. We can say that this here is half of pi or 90 degrees, whatever you want. And then this point here from the beginning would actually be 3 halves, so 3 over 2 pi, which would be 270 degrees. Okay, that's kind of what we teach the kids really quickly. It's sort of an add-on. We don't spend a lot of time on it. And so if we apply this to our question, what we end up with interpreting, let's just shrink this down a bit so we can see, we start to say stuff like, well, it's separated by 60 centimeters, so a few different options. We can put let's go ahead and put the points here. So that's at 0, and then the next point would be 60 would be here. So that's one option. Actually, let me call that, I'll call that A and A. So those A prime. Let's go that. Then we could put the position here, B, and then 60 centimeters on would be B prime. And then we could do C here. And then if we keep going, we'd have a point here, which would be C prime, and so on. So let's look at those differences. A to A prime, well, that's going from this dot here to here. So that's matching up with 3/2 of pi. So let's just put that in for now. So let's go 3/2 of pi. That's going to be the phase difference. And I'm starting to see that on the answer key. I'm starting to see that here. So I'm tempted to go D at this point. But let's keep going. Let's go B. Well, B is this point, and then B prime is also over here. And so that's 1/2 pi, where's my starting point, and then to get to 2 pi, well, I've got to add 3/2 of the wave. So again, that's 3/2 pi. That's my difference. So same again, 3/2 pi. And actually, it doesn't matter what you do. If you divide up the length of the wave, which in this case is 80 centimeters, you divide it into a scale, whatever it is, and then multiply by the ratio, you're always going to get this 3/2 pi. So, from a traveling wave perspective, or if you were looking at two waves that were out of sync, you could very strongly make the argument that the answer would be D. And that is what most people will do. That is what I'm sure most kids are doing. They're looking at this as a traveling wave. They're looking at the wave shift between the two, and they're getting 3/2 pi radians. Now, that's wrong because, and this is where we get into the difference between a standing wave versus a traveling wave, or a single standing wave, a static wave, versus two waves that are out of phase. So this actually isn't asking about two waves that are out of phase. It's asking about a thing that's fixed on the string. And so then we have to think about it differently. There's a different model to use in the way we would describe this. And this is why it's annoying, because nowhere in the curriculum does it tell us that we have to do that. There's nothing in this document that says that we need to consider standing waves versus or fixed waves versus traveling waves, or standing waves versus traveling waves, and the difference between particles or fixed points on the wave versus phase shifts on a traveling wave. It just says phase difference. That's really all it says. And so I find this really annoying, and they do this all the time. There's a bunch of practice questions like this. What they're trying to get at badly is that it's not a phase shift when you're comparing two waves, which is what we were just doing. So if we think of a position or a fixed position, or a particle, or some fixed location on the string, here's what they were trying to get at, and this is why they had it keyed C. If we imagine positions in this loop, okay, let's imagine these are all fixed positions. The phase that they're in has nothing to do with the gradient or anything like that. All it means is that these guys are going to be going down. Okay, so if these are water molecules on a wave, or molecules of string on a string that's vibrating, these are all in the down phase. Whereas these particles, or these positions on the string, are all in the up phase. So this is your classic fixed wave location question, and really all we're asking here is it in phase? Does it match with the reds, or does it match with the blues? Are you on the red team or the blue team? And if you're if it's a red versus blue, then you can see here that the difference between the red and the blue is 180 degrees. So the difference in the phase is either 0 if it's red compared to red, or it's 180 if it's compared red to blue. Of course, 180 is also pi radians. Okay, so let's go back to our scenario. We have 2 points that are 60 centimeters apart. So as we showed in the previous diagram, they could potentially be here and here, or they could be, let's go here to here, or here to here. Either way, the most likely example is that they're 180 degrees out of phase. We're comparing a red to a blue. And so if that's the case, then the answer has to be C, which is what it's marked as. But it's deeply unsatisfying because of all the resources for IB, and it's deeply unsatisfying because of the curriculum document that doesn't distinguish between phase differences on two waves compared to each other versus phase differences on a single standing wave like this. So there's my rant. I don't like it. They do lots of practice questions like this, but there it is. Actually, it's not even rant over, because I managed to find an examiner's report, and check this out. It's quite damning. Here it is. It gives a bit of an explanation as to why, well, pretty loose explanation, blah, blah, blah. But interestingly enough, it tells us, it says there's a low discrimination index. That means they really had no way, that all of the kids that wrote this, they were not able to distinguish between them. D being the most popular answer, that's what we kind of came up with before. Most kids are applying the phase differences of two waves, and they're realizing that the 3/2 pi is the separation difference between the 2 points if you were comparing two different waves. That's what most people will teach. That's what all the resources have. So D is more popular than the key, and the other three answers are spread evenly. So this statistics on this question are just garbage. And again, we could have predicted that, given that they asked these questions without being explicit in the curriculum. Okay, now rant over. I'm pretty sure I'm done. For question 27, I think that was the other one you were asking about. This one I think is keyed correctly. I think this is just a case of interpreting where the energies are in the system. So we have a spring loaded with a mass oscillating in simple harmonic motion. We're given the amplitude of the motion, which I think we probably want to interpret as the amplitude being the displacement, so the x, if we're using the 1/2 kx squared equation for the energy of the spring. E is the energy. What's the total energy of the spring when the mass is increased to 3m and the amplitude increased to 2a? Well, the key understanding here is that it's asking for the total energy of the spring when the mass is increased to 3m and the amplitude is increased to 2a. Well, the total energy is going to be a product of the kinetic energy and the spring energy, but the total energy of the spring, that's assuming that the spring is completely compressed, so it's at its maximum stretch. So let's go ahead and say that's here and here, with this being the equilibrium position. So what we're really asking here is what's happening to the energy at this point. Well, at that point there is no kinetic energy, so we can cancel this right out, and we can just go with this 1/2 k, well, we'll call it a squared, and now you can see that it's just going to be 2 squared coming from the 2a. We're doubling the 2a, we're doubling the amplitude. 2 squared is 4, so we're increasing it by a factor of 4, so it's got to be